Hi everyone, Mr. Coxford here. In this video we're going to be looking at the first law of thermodynamics. So to understand the first law of thermodynamics, the first thing we need to remember is that internal energy, the internal energy of gas or some system, it depends on the temperature of that system. Temperature simply being the average kinetic energy of the particles of a substance, and the internal energy being the total kinetic energy of the particles of a substance. So more internal energy means higher temperature, less internal energy means a lower temperature. Now, we can change the internal energy of a system when we add heat or when we remove heat. To add heat, that means that the system is encountering a temperature that is higher than it. There would be heat transferred to the system, or heat would be removed when it is encountering an environment with a lower temperature, and then heat would be removed. But we can also change the internal energy of a system by doing work on it or by that system doing work. And just remembering that work, there's some force and there's some displacement. So this is different than a heat transfer. There's energy can be transferred in both of these ways. So what we can say is that heat is that the internal energy of a system will change when heat is added or removed, or when work is done on a gas or by a gas. And we say gas in this case, but it could be a system, but we focus on gases a lot in this unit. So what we could say symbolically or with an equation is that the change of the internal energy of a system is equal to the heat plus the work, where we say that Q, positive Q, this is heat that is added to the system, and W, this is work done on the system. And it's important to say added to, heat added to, and work done on, because this defines what is positive heat and what is positive work and what is negative heat and negative work. So positive heat would be added to the system, negative heat would be heat removed from the system. Positive work would be work done on the system, negative work would be work done by the system. Okay, so positive is something done to the system, added to, done on. That's how I always remember it. So here is what the first law of thermodynamics actually states, in not just in symbolic form, but in a sentence. It says that the change in internal energy of a system is equal to the heat transferred to the system plus the work done on the system. And so if we can say a few things, if the system is closed or if it's isolated, then that means that there's no work being done on it and there's no energy gained or lost, there's no heat transferred to or from the system. An isolated system has no change in internal energy. But, and this is the cases that we will be looking at, if a system is not closed, if it's a non-isolated system, the state of the system can change. Work can be done on it or by it, heat can be transferred to it or from it. And then that means that the internal energy of that system will be changing. So let's see how we can apply this first law. And we'll be looking at it for an ideal gas. And if that's the case, then the relationships that we've seen prior for ideal gases, PV equals nRT, and the similar equation will be useful. And so what we're going to be looking at is something called a PV diagram, a pressure volume diagram. And this diagram is actually two dimensions of a three-dimensional diagram. we can actually look at a PVT diagram, which will have 3 axes, but instead of looking at a 3-dimensional diagram, we can use a 2-dimensional diagram, a PV diagram, and still understand what's going on with the temperature on that diagram, and I'll show you how. What we will consider is that changes are going to occur very slowly, which means that the gas will remain essentially at equilibrium in the environment. The pressure, the volume, and the temperature will go through slow changes. There'll be a sequence of points on the PV diagram, so this will look like a smooth curve. So we'll have some lines, some curves on these PV diagrams, and the assumption is that we can move along these lines. Each point on the line will be a point that gas will go through. It will have that specific pressure and that specific volume in its transition from one part on the curve to another part. And we call those reversible processes. Now, in real life, these processes are not reversible, meaning we can't go back and forth along these curves without adding some sort of energy or losing some amount of energy. But we live in the ideal world here in physics where we assume that things are reversible. So here's what a PV diagram looks like. A very basic PV diagram has an x and a y axis. On the y-axis is pressure, on the x-axis is volume, and there'll be some curves on this diagram. I'll draw a few curves, so I'm going to erase them. You might have a curve like this. You might have a curve that looks like this. You might have a line, vertical line, horizontal line. It could be a squiggle. It could be anything, really. One thing to note, a feature of this diagram, is that in this direction, up and to the right, if you are at a location higher up or further to the right, you are at a location that has a higher temperature than a location that is further down or further to the left. Okay, so we would say that temperature increases in this direction. If you are at a location up and to the right from some other location, that means that you are at a higher temperature. If that doesn't make sense, we'll see some diagrams shortly that will make more sense of that. Okay, now let's look at the work done on a gas. What does that mean, that work is done on a gas? So let's look at a very simple example here. You can see this diagram here on the right-hand side where we have a piston that is pushing down into a contained space. So the bottom part here, this is a contained space. No gas can enter, no gas can leave. That means that the number of molecules of gas is remaining constant. And we're going to apply some pressure down on this piston to change the volume of this gas. We can see here that the piston is at some height, and the piston itself has some area. And here are the little molecules of gas within it. Okay, and we're going to apply some pressure, which, if we remember our relationship between pressure and force and area, it means that if we're applying some pressure on the piston, that means that the force that's applied on this gas is equal to the pressure times the area of the piston. Now, let's say we're going to push this piston down some distance d until it's down here. It means all those molecules are now squished in a lot more. They're now going to be in a smaller space. All right. And so the work done on this gas, well, it's simply this force that we're pushing down on the gas with times the distance, right? Our equation for work is force times distance. And subbing this in here, it's the pressure acting on this gas times the area of the piston times the displacement, how far we have pushed this gas down. You might notice a familiar term in there, A times D, the area of the cylinder times the displacement. This is the volume change of the gas. Right here in our gas, this is the change in the volume. How much volume we have increased or decreased, in this case, decreased our gas by. So what we can write this as is that the work is equal to P times the change in the volume. But I'm going to add one little extra thing in here. I'm going to add a little negative sign. Why a negative sign? Well, if we think about this, if I am pushing on this piston, I am decreasing the volume. It means that this delta V term here is going to be negative, but I am doing positive work. My displacement is in the same direction as the force. And so that means that I need this negative sign here to rectify that when I do positive work, I'm getting a negative change in volume. And so the negative and the negative will work out to become positive. So what this means, here's our little equation. This says that work done on the gas is positive if the volume decreases. And this is what we said near the start of the video, is that work done on a gas is positive, and work done by a gas, that would be if the volume is increasing, then we would end up with negative work, and this equation will show us exactly that. Now, in terms of units, let's just make sure our units work out. So we have pressure times volume. Pressure is in pascals, volume is in meters cubed. Pressure from our equation up top here, where it's force divided by area, it's newtons divided by meters squared times meters cubed here, and we end up with, we can see meters squared, and get rid of the squared up there, it ends up becoming meters to the power of 1 Newton meters, which equals to joules. Joules is the unit for energy or work. Perfect. Now, if you wanted to get into the calculus of this, this equation here works really nicely when we have a nice flat line, but when we have a curve, it's not quite so simple. If the pressure is changing and the volume's changing, it's not quite as easy. So what we could do is get into some calculus and say that the work is actually the integral of the pressure times dV. If you don't know anything about calculus, that's fine. This is basically saying it's the area under a PV graph. That is actually kind of useful, and we'll see some examples later on in the video about how that works. So don't really worry about the calculus. Now, let's really just here, I just want to make sure that we have broken down exactly what positive work, negative work, or even no work looks like. So if we have expansion meaning we have an increase in volume, this means that work is done by the gas, and so we call this negative work. Okay, work done by the gas is negative work, and that's delta V. The change in the volume is positive when we have expansion. For compression, compression is when we do work on the gas. Work is done on the gas. And this is positive work. Compression is when delta V, the change in volume, is negative. And if we were to have constant volume means there is no pushing of the gas in either direction, there's no displacement, that means that no work is done. Because delta V is equal to 0. And our equation there at the top of the screen right now, work is equal to negative P delta V. If delta V is 0, there's no work done. That's another way to justify it.